carboxylic acids are acids, and we remember that an acid is a molecule that is able to donate a proton to a base. So carboxylic acids all have the same structure. This Cu group, C, the carbonyl carbon, is also bonded to hydroxyl, and this hydrogen on the hydroxyl is the acidic hydrogen. So when that proton is donated, carboxylic acids have a similar structure for their conjugate base. They've lost that acidic hydrogen. They have a negative charge, COO minus. And that conjugate base that's formed is known as a carboxylate anion. Now let's take a look at these two equations of two different carboxylic acids dissolving in water. On the top we have acetic acid, and when a weak acid dissolves in water, it actually reacts with water because water is a base. So a weak acid will donate a small amount of protons to a small amount of water molecules to form hydronium, cation, as well as the conjugate base. So in a weak acid, the equilibrium is always favored on the side of the weaker acid and weaker base. So in both of these cases, acetic acid and pyruvic acid is a weaker acid than hydronium. So both of the equilibrium for both these chemicals will be on the left. So these are weak acids, only a small amount of acetate and hydronium is formed. And the same thing with pyruvic acid. It is a weak acid, only a small amount of pyruvate and hydronium is formed. And I just want to point out the name of the carboxylate anion. It ends in ate. So acetic acid, acetate is the conjugate base. Pyruvic acid, pyruvate is the conjugate base. And let's remind ourselves how we rank or classify the strength of weak acids through Ka. And Ka is the equilibrium constant for the dissolving of acids in water, and it is the concentration of the conjugate base multiplied by the concentration of hydronium divided by the concentration of the undissociated acid. And for any weak acid, the concentration of the undissociated acid is going to be higher than the concentration of the conjugate base, carboxylate anion for carboxylic acids, and hydronium. But rather than look at Ka values, we look at pKa values. And pKa is equal to the negative log of the Ka. So it's a little bit like pH in that the higher the pKa, the weaker the acid. Sort of like with pH, the higher the pH, the less hydronium there is, because it's the negative base 10 log. So you will be expected on an exam and on your homework to rank different acids based on their pKa. So a low pKa, such as that for trichloroacetic acid, means it's a stronger weak acid than formic acid, which has a Ka of 3.74. So the acid with the highest pKa will be the weakest, and that with the lowest pKa is the strongest. And then also notice here oxalic acid and glutaric acid have 2 Ka values. That's because they're dicarboxylic acids. So this first Ka is the Ka when the first proton is removed, and then the second one is when the second proton is removed.